All right, so now we're going to be discussing this notion of holonomy, or what the book refers to as this round-the-world transport vector. Okay. So the basic idea, if you will, is that, as you recall, we alluded to this idea that parallel transport of a vector along a curve is in general path dependent. Okay, so you could imagine what happens if you have 2 points, but you parallel transport along 2 different paths. Okay, and our claim is that in general, these 2 different parallel transports will lead to along 2 different paths, it's like will lead to different answers, right? So another way of sort of thinking about that, instead of going through 2 different paths, is to imagine going, forward in one path and then backward in the other, and then you get to a single point, and you can ask yourself whether that vector has changed. It's like under this sort of round the world type trip, this round trip, it's like which we've talked about. Okay, and so the idea is that, so in general, parallel transport is path dependent. Right. So we can also sort of also think about this in terms of what happens when you sort of parallel transport sort of along a closed path. Okay. So let me sort of give you some intuition for this. Imagine I have my thumb sticking out. It's like, and the direction of my thumb is like a tangent vector to, say, the surface of a sphere. And I move my arm in this kind of spherical triangle, and I come back. And you'll see that when I started off, it's like I had my thumb pointing up, and I sort of do the obvious thing as I move along the spherical triangle. And by the time I've come back to the initial position, my thumb has rotated. So this is an example of holonomy, or an example of doing parallel transport along a closed loop and getting some non-trivial action. It's like on that tangent space. Okay. So why is that of interest? That's of interest because basically that's a way of quantifying in some precise way how curved the space is. Okay. So imagine if you did this parallel transport thing again on a flat surface, nothing really happens to that tangent vector, right? It stays the same. So this notion of holonomy is going to be related in some way to the notion of curvature. So the notion of holonomy, which is sort of the extent to which the tangent vector rotates, right, as you move around a closed loop, right, is going to be related to the curvature of the manifold. Well, actually, of the connection, if you will, right? Okay. So this curvature term is then going to be referred to as this Riemann curvature. All right. So this is the Riemann . Okay. So anyway, so the bottom line is that, it's like you can try to think of this as either going around in a loop, in a closed loop, or, going along 2 different paths, right? So in either case, you either come back. So on one hand, you could come back to the original point, or you could go to a new point, but in 2 different ways, right? Okay, so let's see what happens when we try to do something like that. Okay. So we have a curved space, and then we have some sort of infinitesimal sort of quadrilateral. Okay, so let's say we have P, Q, R, and S. Okay, and I move sort of along two paths. I could go from P to Q and Q to R. I could go from P to S and S to R, right? So those are two different paths, right? And I can sort of take a tangent vector at P, which I denote by A, and I can move along that, see what happens. Okay. Okay, so P, I'm going to have some coordinate system coordinates, which I say is c. Q is going to be c plus, say, d1 c. All right, and then S is going to be c plus d2 c, and then R is going to be c plus d1 c plus d2 c. All right, and then all these are thought of as being infinitesimal. It's like, and so it actually makes sense to just add these things. Okay, and this is going to be a plus d1a. This is going to be a plus d2a, and then this is going to be a plus d1a plus let's call that delta 1 2a, and let's see what happens. Okay. All right, so as I said, we're going to start with A. We're going to parallel transport along this path to Q, and then from Q to R. We're going to compare it to parallel transporting A from P to S, and then from S to R. And then we're going to look at what the difference is. Okay, so let's see what happens. Okay, so A, which is in T c, right, goes to A1, which is A plus D1A, which is in the tangent space to c plus D1 c. And you can write what this is. D1 AI is equal to minus the connection JK I of AK D1 c J, right? So if you recall, it's like this is a linear functional, right? Well, it acts linearly. It's like it acts on this components. It's like of the vector which you're parallel transporting, and it depends. It's like on what point you're moving to in a linear way, right? So this is what that expression is. Okay. And then I can parallel transport A1. It's like from Q to R, right? So I can parallel transport A1 from Q to R along this path, which I call D2 C2, right? So imagine that I'm moving in the same direction as this, right? Okay, so that means that delta 1 2 of AI is going to be minus gamma ijk c plus d1 c, right? So this is what, so this is the new point, and then it is transporting this object by d2 cj. Okay, so I can Taylor expand this. Okay, so what's going to happen, right, is that when I Taylor expand this object, I'm going to involve derivatives, partial derivatives of the connection coefficients. Okay, so I'm going to Taylor expand this gamma ijk term, right? So that's equal to minus gamma ijk, right? Okay, so this is the leading order term, right? So this has none of the infinitesimal terms, right? Then I'm going to differentiate this. So this is minus dl gamma ijk d1 cos cl. So I'm essentially, perturbing. It's like this thing. It's like in this direction, right? So that's why I have d1 cos cl here. It's like paired with the partial derivative with respect to the alpha component, right? So this is the leading order correction. It's like to the connection coefficient due to the fact that I'm not evaluating it cos c, but evaluating it cos c plus d1 cos c, right? Okay, and then the rest of it stays. You have this d2 cos cj term and then the ak term, right? So we're just taking, it's like, only one infinitesimal, right? Because, again, the infinitesimals are supposed to be very small. It's like, and then more or less what happens is that when you square the infinitesimals, you pretend they don't exist. So you just, essentially, another way of thinking about this is that you're taking the Taylor expansion of this to leading order, to this first order. Okay, all right. And then what I can do is I can just look at the d1ak term. So this is gamma ijk and then this term, right, if you recall, it's like also involved a connection term with a minus sign, so that becomes a plus, right? And then this gamma lmk d2 cos cj d1 cos cl am. Okay, so all I'm doing basically is that I'm looking at this d1, it's like ak term, and I'm writing it, it's like in terms of this first equation which I got, in terms of the connection, in terms of the components of A, in terms of this d1 term, right? All right, so that accounts, so I'm going to take this times this term times this term, and that's what I end up getting. All right, so that gives me the parallel transport of A from P to Q and then from Q to R, right? I can do the reverse, and when I do the reverse, I can compute what this is. Okay. So I can compute that delta 21 AI, right, is going to be very similar, but sort of with a bunch of the ones and twos here sort of reversed, right? JKL, sorry, this is D, this is D2, I'm sorry. All right, okay, yes, so this then would be D1 CJAK, right? So instead of a 2 here, I have a 1 here, right? Minus DL gamma JKI D2 cos L D1 cos I AK plus gamma JKI gamma LMK of D2 cos C all right, so I'm sorry, this should be, yeah, okay. All right, so anyway, so that tells you, that gives you a characterization of what happens when you parallel transport from P to S and then from S to R, right? So, all right, so it's a directly analogous calculation from what I've done here and here. So I'm not going to worry too much about the details. So you can ask then, given now two ways of parallel transporting the vector A, it's like from the point P to the point R, right? One going through this loop and the other one going through this curve. You can ask what the difference is, right? So, so the difference, right, is given by, let's call that delta AJ, which is R JKL I AL D1 cos CJ D2 cos CK minus D1 cos CK D2 cos CL. Right, where, so we've introduced, it's like this new tensor. Well, it's going to turn out to be a tensor. In particular, it's going to turn out to be what's called the Riemann-Christoffel. It's like curvature tensor. Okay, but anyway, so for now, it's like you can sort of see, it's like from the terms which show up that it involves the connection coefficients and involves derivatives of the connection coefficients and involves sort of this, you know, quadratic combination, if you will. It's like of the connection coefficient. So it's actually a contraction of it. See, it's contracted from this upper index with this lower index. Okay, so anyway, so that object, this Riemann-Christoffel curvature, is given by the following. So it involves these partial derivatives. It's like of the connection coefficients, and involves, yeah, so this term here cancels out, right? Not too surprisingly. Okay, and then it involves this contraction of the connection. Okay, right, so the repeated index here is m, right? There's an up m and lower m here, there's an upper m here, sorry, upper m here and a lower m here. So there's a implicit summation via the Einstein summation convention. All right, so this is going to be what is called the Riemann Christoffel curvature. And it's going to turn out to transform as a tensor. So it's going to be the Riemann Christoffel curvature tensor. Okay. So you can think of this small loop, if you will, as an infinitesimal, right? So we can denote the infinitesimal loop by a tensor. Okay, so let's denote this as df jk. So this is equal to d1 cos Cj d2 cos Ck minus d1 cos Ck d2 cos J. And this is antisymmetric with respect to the two indices. So this antisymmetric with respect to the indices Okay, so what that means is that dfij is equal to minus dfji, all right? So you can think of this as a small surface element. All right, so if you know something about differential forms, you can think of it as a differential two form in a sense, something like that, okay, morally speaking. And then what happens is that you can think of this change in the, it's like in this sort of the parallel transported object, right, as being this Riemann curvature tensor. It's like paired with this infinitesimal loop element. So I'm just sort of taking this thing into parentheses and thinking of it as being like an area form, if you will, right? So so this becomes RJKL I A L D F J K. So so far we've talked about what happens if you if you do this parallel transport over this infinitesimal loop, right? And so you can ask, well, what happens if you sort of do a parallel transport over a large loop, okay? And then what happens is that that infinitesimal change, it's like becomes sort of a finite change, and as you might expect, it's like you can write it as some sort of surface integral. So for finite loops, right, you can say that this finite change in the AI is the integral, is the surface integral of this curvature tensor times the vector, and then with this area form. Okay. And the point is that this doesn't depend on how you go about spanning this surface, and this is true because of the Stokes theorem, right? So this is independent of how we span the surface. And this comes from sort of this generalized Stokes theorem. Okay. Right. So, all right. So this gives you this idea of holonomy, which again the book refers to as this round the world transport, right, of the vector. All right. And again, the upshot, if you will, is that if you parallel transport around a closed loop, or you parallel transport along two different paths to the same final point, and the answer is different, right? It's path dependent, and this is an indication that the object, the manifold you're working with, is curved, all right? And you can measure, it's like the amount of curvature using this Riemann-Christoffels curvature tensor, which is expressed in terms of partial derivatives of the curvature of the connection coefficients, as well as this contraction. It's like of the contraction of the connection coefficients in this way. Okay, and as you might expect, if the converse is true, that if this Riemann-Christoffel curvature tensor is it vanishes, right, then there's a sense in which the manifold is locally flat, and you can introduce locally flat coordinates on that manifold. Okay, so let me just stop here for now.